Many applications like sports gear and transport systems demand low weight, which depends partly on material density. Density is a mass per unit volume and is measured in kg per meter cube. Choosing low density materials help reduce overall weight without compromising performance. Atoms vary widely weight but only slightly in size. In solids, the heaviest stable atom uranium with an atomic weight of 238 is about 35 times heavier than the lightest lithium at 6.9. Yet, their diameters are nearly identical at around 0.32 nanometer. Even the largest atom, cesium, is only about 2.5 times bigger than the smallest beryllium. This means that a material's density is determined primarily by its atomic weight, with atom size and packing arrangements are playing a smaller role. Metals are dense because they consist of heavy atoms like iron tightly packed together. Polymers, on the other hand, have low densities due to their light elements, mainly carbon and hydrogen, and their loose molecular structure. Ceramics typically fall in between, made from light atoms like silicon, oxygen, nitrogen, or carbon. The lowest density, below 1 mg per meter cube, are found in forms where much of the volume is just empty space filled with air. Atoms in metals often pack like tightly arranged spheres similar to billiard balls set on a table. This dense arrangement is called close packing, and it happens in three dimensions in two main ways: hexagonal close packed with ABAB stacking sequence and face center cubic with ABC-ABC pattern. Both structures have the same packing efficiency of 74% space filled. Another structure, the body-centered cubic, has a low packing efficiency of 68% and is formed by stacking square-packed layers. This is typical of iron and many steels. These atomic arrangements repeat in space, forming unit cells that build a crystal lattice, where atoms or group of atoms are attached at lattice points to create a regular and repeating 3D structure. Polymer structures differ significantly from metals. They consist of long chain of carbon atoms with attached side groups. In thermoplastics, these chains are held together by weak bonds that melt easily, allowing the material to be reshaped when heated. While full alignment of this long chain is rare, small aligned segments from crystallites that scatter lights. Polymers without crystallites like polycarbonate, PMMA, and polystyrenes are transparent, while those with partial crystallinity like polyethylene and nylon are translucent due to light scattering from these crystallites. A major transformation in polymers occurs when chains are cross-linked, replacing weak hydrogen bond with strong covalent carbon-carbon bonds, creating a large interconnected network. Elastomers like rubbers have relatively few cross-links, giving them flexibility, while thermosets like epoxy and phenolics have many, making them stiffer and stronger than thermoplastics. However, these cross-links are permanent. Once set, thermosets cannot be melted or reshaped, making them non-recyclable. Most engineering materials are mixtures of different elements rather than pure substances. When these elements dissolve into each other in solid form, they create what's called a solid solution. Examples include brass, solders, and stainless steel. Composites are materials made by embedding fibers or particles into continuous matrix. This matrix can be polymer, metal, or ceramic. These materials offer high stiffness and strength relative to weight, with MMC and CMC also excelling in high temperature environments. The density of composites with no porosity is calculated using the rule of mixtures based on volume fraction and density of the reinforcement and matrix. So, from dense metals to lightweight polymers and advanced composites, The internal structure and atomic arrangement of materials define their unique properties. Whether it's a closed-packed crystals in metals or cross-linked networks in thermosets. Understanding the structure helps us to choose the right material for the job. Fascinated by density and curious about more? Share your thoughts in comments or email us. Subscribe to Material Engineer for more video on density and science of materials. Don't forget to hit the bell. Until next time, keep learning, keep asking, and keep exploring.